In section 2.6, we look at implicit differentiation and related rates. So implicit differentiation is needed whenever you have an equation with, let's say, y's and x's, but the equation is not solved for y already. And so what we want to do is we want to take the derivative implicitly with the derivative of y with respect to x. Now, when we do that, we're going to multiply by dy dx whenever we take the derivative of y. And this is really because of the chain rule. We're always taking the derivative in this part of this section with respect to x, and y is considered to be a function of x, even though it's not written y equals. So let me just show you how this works with example number 1. Find the derivative dy dx if y cubed plus x squared is equal to 3x. So let's start by taking the derivative of y cubed. The derivative of y cubed is 3y squared. But you just took the derivative of y, so we're going to multiply that by dy dx as part of the chain rule. You're thinking about y having this inner relationship with x where there's some underlying function of x, and so you need to represent that you've taken the derivative of that by saying dy dx. Plus, the derivative of x squared is 2x. Now notice that we don't write anything after this. We're taking the derivative with respect to x. Let's pretend if we were to write something that indicates we took the derivative of the x, it would be dx dx. But that's the change in x divided by the change in x, which is just 1. So we don't write that. We just leave that piece out and alone. And that's equal to the derivative of 3x, which is just 3. Now we're solving for dy dx, this piece right here. So we move and just solve it dy dx just like it's a single variable. So we move things over and divide like normal. So we get 3y squared dy dx is equal to 3 minus 2x, and dy dx is equal to 3 minus 2x over 3y squared. And that is a formula for the derivative. But notice that it's not a function of just x, it's a function of both the x and the y. So there are cases where when you have this implicit type equation, you're going to need both an x and y coordinate to evaluate that derivative. But on the other hand, it still is a derivative. It still means the slope of the tangent line at a point and the rate of change of a curve like such. Let's look at example number 2. The equation of a circle centered at the origin with radius 5 is x squared plus y squared equals 25. The point 3, 4 lies on the circle. Find the equation of the line tangent to the circle at point P. So let me go ahead and draw in the line tangent at point P. So let's start with the equation of the circle. And we want to find the derivative. Since it's not y equals, we'll have to take the derivative implicitly. So this is going to be 2x plus 2y. And you just took the derivative of y, so we have to multiply by dy dx. And that's equal to the derivative of 25, which is 0. Solve for dy dx. We start by moving the 2x to the right side and then dividing by 2y. The 2's cancel, and it leaves us with negative x over y. This is the formula for the slope of the tangent line. Next, we want to find the slope of the tangent line. To do that, I'm going to use the evaluation bar, and I'm going to evaluate at the point 3, 4. That means the x is 3, and the y is 4, using this formula, negative x over y. So the slope of the tangent line is negative 3/4. Finally, we find the equation of the tangent line. We have the point, we have the slope, so we use the slope-intercept form, and we get 4 is equal to negative 3/4 times the x value of 3 plus b. And when you work that out, you get b is equal to 25 over 4. So the equation of the tangent line is y equals negative 3/4 times x plus 25 over 4. Example 3. Find the slope of the tangent line to 3x over x plus y squared equals 9 at the point negative 6, negative 2. So the first thing we need to do is take the derivative of this equation. And to do that, we need to use the quotient rule. So we take the derivative of the top, the derivative of 3x is 3, times the bottom unchanged. So notice that since the bottom is unchanged, we did not need the dy dx in this part. We did not actually take the derivative of y. We're just using the y unchanged. Minus, now we take the derivative of the bottom. The derivative of the bottom is 1 plus 2y. And at this point, I did take the derivative of y. So we're going to multiply by dy dx right there. Now notice that it's just 2y times dy dx. It's not the entire expression 1 plus 2y that is being multiplied by dy dx. It's just the 2y part. Continuing with the quotient rule, we multiply by 3x. Then we divide by x plus y squared, quantity squared, is equal to the derivative of 9 is 0. Now let me simplify this just a little bit. I'm going to distribute the 3 and get 3x plus 3y squared minus 3x minus 6xy dy dx over x plus y squared squared. Next, I'm going to simplify the top a little bit. We have 3x and minus 3x, and those can cancel. And this leaves me with 3y squared minus 6xy dy dx over x plus y squared squared is equal to 0. And now we want to find dy dx. Now we could continue to try to solve the equation, or you could just plug in the point right now. So we know that the coordinates are negative 6, negative 2. So if I plug that into this equation, I get 3 times negative 2 squared minus 6 times negative 6 times negative 2 times dy dx over negative 6 plus negative 2 squared, quantity squared, equals 0. This gives me 3 times 4 minus 72 dy dx over 4 is equal to 0. Then we have 12 minus 72 dy dx is equal to 0. I'm going to cross multiply the 4 over here, and that's going to wipe out that 4 and make 0. So we now have 72 dy dx, that's negative, is equal to negative 12. And so dy dx is equal to 1/6. Let's look at example number 4. Find the slope of the tangent line to y times the square root of x squared plus y squared is equal to 65 at the point 12, 5. So first thing to notice is that in the equation, we actually have a product. We have y times the square root of x squared plus y squared. So we'll need to use the product rule to take the derivative. And so here we go. The derivative of y is 1 times dy dx times the square root of x squared plus y squared unchanged plus the derivative of the square root of x squared plus y squared. So that's going to be 1 over 2 times the square root of x squared plus y squared times the derivative of the inside, 2x plus 2y times dy dx times the original function on the left, the y, and then equal to 0, the derivative of 64. All right, now we need to simplify. So we're going to have the square root of x squared plus y squared times dy dx plus, and then we're going to have 2xy plus 2y squared dy dx over 2 square root of x squared plus y squared equals 0. Now notice in the fraction, I can factor out a 2. So this left part is the same still. And let's factor out the 2. So it's going to be 2 times xy plus y squared dy dx over 2 square roots of x squared plus y squared equals 0. 2's cancel. And that leaves me with x squared plus y squared dy dx plus xy plus y squared dy dx over the square root of x squared plus y squared equals 0. Next, I'm going to multiply both sides by the square root of x squared plus y squared. When I do that to the left term, the square root of x squared plus y squared gets multiplied by itself, and that leaves me with x squared plus y squared times dy dx. And when I do it on the second term, it just cancels the denominator. And in fact, that denominator is the reason I chose to do this, in order to get rid of it. And of course, on the right side, 0 times the square root of x squared plus y squared is still just 0. Now we can, I think at this time I'm just going to plug in the numbers. So I'm going to plug in 12 and 5 into the equation and then solve for dy dx. So this is going to be 12 squared plus 5 squared times dy dx plus 12 times 5 plus 5 squared times dy dx equals 0. 12 squared plus 5 squared is 169 times dy dx. 12 times 5 is 60. And 5 squared is 25. So it's 25 dy dx is equal to 0. Combine the dy dx terms, and we get 194 dy dx. Move the 60 to the right side, get negative 60. And we get dy dx is equal to negative 60 over 194, which reduces to negative 30 over 97. And that would be the slope of the tangent line. Now, it's just asking for the slope, not the entire equation, so that's where we stop. Our next topic is related rates. And basically, related rates examines how one aspect of some situation changes when you know how another aspect of the situation changes as well. Examples of this would be like, how fast does water leak out of a hole when the hole is getting bigger at a certain rate? Well, certainly if the hole is getting bigger, then more water is going to come out. And then how is that rate related to the rate that the hole is changing? Things like this. I've written down some fairly concrete standard methods for you to use to help guide you to solving related rate problems. First off, read the question. Number 2, draw a picture when applicable. Number 3, create your variables and describe them in words. Use both the regular variables and the rate variables and mark the quantity that you are solving for. Create the equation or equations needed for the problem using the variables that you created. So when you create the variables, you are verbally describing what the variables represent. Then when you create the equations, you're using those variables in your problem. Number 5, differentiate implicitly with respect to time t. Differentiate means to take the derivative, but instead of saying d something dx, all of these problems are going to be d something dt. So what's happening here is, even though t is not going to be one of the variables we're using in the equation, we are differentiating with respect to time because things are changing over time. How fast is the hole opening? How fast is the water leaking out of the hole? All of those rates are going to be the derivative taken with respect to time. Number 6, substitute values for the regular and the rate variables. And 7, solve for the variable that you need. Example number 5. The sides of a square are increasing at a rate of 3 centimeters per second. How fast is the area changing when the sides are 10 centimeters? So, step 2, that was step 1, read the problem. Step 2 is to draw a picture. So we have a square here. And we know that that square is increasing in size. All right, so we can sort of draw it like this. We can leave one point fixed and say it's sort of expanding out this way and that way and stuff. Step 3, create your variables. So the variables I would create for this is s, and that's equal to the side of the square, a for the area of the square, and then I want the rate variables. So the rate variables are found by differentiating each of these variables with respect to time. So we get ds dt is equal to the rate of change in side of square. And that's how you do the description. You just throw in a little rate of change in whatever the variable represented. And then dA dt is equal to the rate of change in area of square. Now let's mark each of these variables with information that we know. So at the point of interest, right, so the square is going to start expanding, and we want to know what happens when the square reaches a side length of 10 centimeters. So let's put that in here. We know that the side of the square is increasing at 3 centimeters per second. That's a rate. That means that's the derivative. So that's ds dt, 3 centimeters per second. How fast is the area changing? Well, how fast would be a rate, and we want the rate of the area. So that would be the rate of change in area, which is dA dt. So this is the one that we are solving for. Now we didn't mark A, and we were not given the number A explicitly. We could find it, and we could put it in there, but there's a chance that we may not even need it. So we'll just leave it, and then we'll put it in if we have to. Step 4, create the equation needed for this problem using the variables that we defined. Well, we need area because we're talking about the area of a square. And what is the area of the square based on the side? That is A is equal to S squared. That is one that you'll need to know for this course. Part 5, differentiate implicitly with respect to time. So the derivative of A is just dA dt. And the derivative of S squared is 2S times ds dt. Part 6, substitute in the values that we know and make sure we get the one that we're looking for. So we're looking for dA dt. So everything is set up for that. And then we're going to have 2 times the side, which is 10 centimeters, times ds dt, which is 3 centimeters per second. And you multiply that out. 2 times 10 times 3 is 60. Centimeters times centimeters would be centimeters squared divided by S. And that's the answer. Now notice how the units just make sense with this problem. We're looking for the change in area per unit of time because it's dA dt, and centimeters squared is an area unit, and per time would be the division by the time. It just works out beautifully. Works out great. One other thing to notice is that the area isn't changing at a constant rate. This is how fast the area is changing when the sides are 10 centimeters. But if the sides were 20 centimeters, then there would be a much more bigger change in area. Example number 6. A pipe bursts, creating an oil spill on the ocean, resulting in a circular oil slick. The oil is flowing from the pipe at 15 cubic feet per minute. The oil slick is 2 inches thick. How fast is the radius of the oil slick changing when it is 120 feet? All right. Step 2, let's draw a little picture. So we have the ocean, right? Maybe I'll draw a little ocean here. Like that. And on the ocean, we have the oil slick. The oil slick is a circle, so I've drawn it in perspective here. And then what's interesting is that the oil is always a circle, and it's expanding out from the center, like so. There we go. All right. Step 3. What are some variables? So we need to figure out what the shape is. We know that it has a radius and it has a thickness as well. It's a circular. So that would suggest that it's actually sort of like a cylinder. Now, you normally think of a cylinder that looks something like this. And that's what we've got here, but it's like really flat, like that. And so that's our model, is a cylinder. So let's think about the items that we need for a cylinder. We need radius. We need height, which is thickness. And we need volume. Volume is the amount of oil in the slick. Then we need the derivative variables. We need dr dt, which is the rate of change in radius. We need dh dt, which is the rate of change in height or thickness. And then we need dv dt, which is the rate of change in volume. Now, what pieces of information do we have? Let's read the question again. A pipe burst, creating an oil spill on the ocean, resulting in a circular oil slick. The oil is flowing from the pipe at 15 cubic feet per minute. All right, 15 cubic feet per minute. Well, the per minute part tells me that it's a derivative because it's a rate. And then 15 cubic feet, well, cubic would be volume. So this must be dv dt. And that makes sense because that's the change in volume going into the oil slick from the burst pipe. Next, it says that the oil slick is 2 inches thick. Well, that would be the thickness or the height. So that's 2 inches. And we're going to need that to be in feet. So that's going to be 1/6 of a foot. But that also tells us something else, right? It doesn't say that the thickness of the oil slick is changing. So that means dH dt is actually equal to 0. It's a constant, right? The thickness of the oil slick maintains its constant thickness, so it doesn't have change, so it's 0. Lastly, the question is, how fast is the radius of the oil slick changing? So that's dr dt, when the radius, is 120 feet. So we put 120 feet up by the radius. All right. Step 4, we need the equation. So the equation of a cylinder's volume is pi r squared h. I would give you that one. That one's a little complicated. But there's something else going on here. Remember that the h is constant. So we can actually simplify this work a little bit by putting in the h as a constant. So it's pi r squared times 1/6 foot. And then that can go into the front. So it's 1/6 pi r squared. And then we already know that that's going to be feet, but we'll leave that off. So that's actually the volume formula for this particular case of a cylinder where the thickness doesn't change. Only the radius is changing. Alrighty, step 5. Differentiate with respect to time. So the derivative of v is dv dt. 1/6 times pi is a constant multiplier, so it stays. And now we just take the derivative of r squared. The derivative of r squared is 2r times dr dt. That simplifies to pi r over 3 dr dt. Now recall our numbers and what we're searching for. We're actually looking for dr dt. So you could solve this equation for dr dt right now, or you could just plug in the numbers and solve afterwards. So we have 15 cubic feet per minute is equal to pi times 120 feet divided by 3. There was another foot involved when I put in the 1/6, so I'm going to go ahead and put that one in now. And then times dr dt. Then solve this for dr dt, and you get 0.119 feet per minute, or you can convert that to inches, and it would be 1.43 inches per minute. Example 7. When the price of dog collars is $P per collar, the manufacturer is willing to supply X hundreds of collars to market, where x squared minus 8x times the square root of p minus 2p squared is equal to 48. How fast is the supply changing when the price is $4 per collar and is increasing at 10 cents per week? All right, so step 2, draw the picture. Step 3, declare your variables. So x is equal to supply, and p is equal to price. So dx dt is equal to the rate of change in supply, and dp dt is equal to the rate of change in price. Let's write down the information that we have. How fast is the supply changing? So the rate of change in supply is what we're looking for. If the price is $4, so price is $4, and is increasing at 10 cents per week. So we need to change that to dollars, so it's going to be $0.10 per week. All right, part 4, use the equation. So our equation was x squared minus 8x square root of p minus 2p squared equals 48. Step 5, take the derivative with respect to time. So the derivative of x squared is 2x dx dt. Oh boy, now we got a problem. All right, let's look at this one. This is negative 8 times x times the square root of p. So that's going to need a product rule. So here's what I'm going to do. I'm going to leave the negative 8 on the outside. Then I'm going to use the product rule on the inside. The negative is with the 8 and will distribute eventually, so we just run this like normal and don't worry about it. The derivative of x is 1x dt times the square root of p, unchanged, plus the derivative of the square root of p, which is 1 over 2 square roots of p, times the derivative of the inside. The derivative of p is dp dt, times the left function, the first function, unchanged, which was just x. So that's the derivative of that product. Continuing, we get minus 4p times dp dt is equal to the derivative of 48, which is 0. So that's the derivative. It's very complicated. You need to take it one step at a time whenever you do that. But now we have another problem. Our next step would be to plug in the numbers that we have. The first thing I need to plug in is x, and guess what? We don't have x. Where can we get x? Well, x is the supply based on the price. The price is $4, and the equation that tells me what the supply is based on price is the original equation. So we're going to have to solve. So let's write this down. Problem is we need x. So we're going to use the original equation, plugging in the p, $4, and then solving for x. So we're going to get x squared minus 8x times the square root of 4 minus 2 times 4 squared equals 48. This gives me x squared minus, the square root of 4 is 2. 2 times 8 is 16x. 4 squared is 16 times 2 is 32. So that's minus 32 equals 48. Then we have x squared minus 16x. It's a quadratic, so I need to move everything over to the left and factor. So 32 and 48 is 80. So that's going to be minus 80 equals 0. This factors with x and x. And then what two numbers multiply to give you 80 and subtract to give you 16? That would be 20 and 4. The 20 is negative, the 4 is positive. And then when you set these equal to 0 and solve, you get x equals negative 4 and x equals 20. X equals negative 4 is not a valid supply number. You can't supply the market with negative 4 dog collars. Or negative 400 dog collars, whatever. So the only number we get here is the 20. So that's actually what our x was, and we can plug that back in up here if you want. And now we can continue the problem. So that was an aside kind of thing, something that we needed to do before we went further. All right, let's see if we can get this all in here now. So this, So this is going to be 2 times 20 times, we're looking for dx dt, minus 8 times dx dt times the square root of 4, because p is 4, plus 1 over 2 square roots of 4, times dp dt, that's 0.10, times x, which is 20, and then minus 4p dp dt. So it's minus 4 times p, which is 4, times dp dt, which is 0.10. All that's equal to 0. So that gives us 40 dx dt minus 8 times 2 dx dt. Now, notice this right here. 20 times 0.10 is just 2. So that 2 cancels with that 2. And that leaves me with 1/2, which I'm just going to write as 0.5. Because I know we're going to get decimals in this somewhere. Minus 4 times 4 is 16. And so 16 times 0.10 is 0.16. That's equal to 0. Let's distribute the negative 8 now. So we get 40 dx dt minus 16 dx dt minus 4 minus 1.6 equals 0. Let's combine the 40 dx dt and this negative 16 dx dt. That's going to be 24 dx dt's. Negative 4 minus 1.6 is negative 5.6. We'll move that to the other side and get positive 5.6. And then we divide. So we get dx dt is equal to 0.233. But remember that x was in hundreds of collars. So the interpretation here is that supply is increasing at 23.3 collars per week. Wolf. All right, that's it. Thanks for watching.